Okay, this is notes for function operations. Learning objectives for today are going to be to add, subtract, and multiply and divide this word functions. This is an important word that we've talked about in Algebra 1. We talked about in the first unit. I'm going to introduce you to a notation that was talked about in Algebra 1 pretty often. Well, I'm sorry, not very often at all, but it's going to be talked about pretty often in Algebra 2. And then we have something that's called composite functions. So when we do this, like I said, here are your Common Core standards, and here is the actual kind of jumping into the whole function notation. Thing that I have found is that when people look at this, they tend to kind of freak out a little bit because of this whole notation here. The f of x and the g of x, it's one of those things that you should not be intimidated by it, because here's what it means. So in Algebra 1, what you guys had was y equals mx plus b. Most people remember that because we dealt with that in the first unit. Y equals mx plus b, here's an example. Let's say we had y equals 3x plus 2. The thing that, again, people kind of look at this notation, and the first word that comes to mind, among other things, is yikes. And the main reason is because it looks really complicated. But all I'm telling you is that the y of the y equals mx plus b can actually be replaced by this notation f of x equals 3x plus 2. And the reason this is because this is notation that wherever I have an x value, I can actually plug in and show what x value I'm plugging in. And you'll see that in the operations that we're going to do in this section. But the main thing that you need to remember and need to not worry too much about is that your y is the exact same thing as f of x. Okay, so in this case we have f of plus g of x. In the addition property, you can say you have an f of x plus a g of x. These could be two functions that you're just adding together and simplifying. The subtraction, you have f minus your g of x. That's stated as f of x minus your g of x. Multiplication, this dot here means you're multiplying the two. That's going to be very similar to compositions, which has an open. We'll talk about that when we get to compositions. But here, you're multiplying the two. F times g of x can be stated as f of x times g of x. And again, all these are two functions. It could be y equals something, y equals a quadratic, y equals a linear, and you're adding the two, you're subtracting the two, you're multiplying the two. You can also divide the two. So you have the division symbol here, divide f over g, or f divided by g of x is equal to f of x over g of x. This notation here has to be stated anytime you have a fraction, because you cannot have a 0 on the bottom of a fraction. It is undefined. So that's why it says g of x cannot equal 0. So we're going to dive right into this. And what I've done is I've tried to color code this to kind of make it a little more user-friendly, let's say. So what I have is I basically have y equals 3x plus 6. And remember, your f of x is a fancy word or fancy way of saying y. My g of x could be another y. So y1 or y2 is equal to x plus 2. But instead of saying y, y1, y2, y3, so on and so forth, we say f of x, g of x, h of x, and we can use different parts of the alphabet. So all this basically is saying, and again I told you I'd color code it just to make it a little bit easier. So we have our f of x. My f of x is in blue. So I look and see over here what my f of x is, and that's equivalent to 3x plus 6. So all I'm going to do is I'm just going to replace f of x is going to become 3x plus 6. I substitute it. I'm going to keep the plus sign in the same color. So plus sign stays the same. And then the next thing we have is your g of x. So my g of x in this case is this guy right here, is equivalent to x plus 2. So all I'm going to do is I'm going to take my g of x and replace it with x plus 2. Now here, this is an Algebra 1 problem. You basically have to simplify it. So you collect like terms. Notice there's not an equal sign. So you're not solving for x. You're just collecting like terms. So I have 3x's and I have one more x. That means I have 4x's. I have 6x and 6 and I have a 2. So I add those together and I get 4x plus 8. and then I'm done. That's fully simplified. The other thing, if you see, I have my like terms, my underlying like terms. That kind of helps me visualize what the like term set is for each one of these. So your answer, your final answer is going to be 4x plus 8 is what the two functions added together simplifies to. Okay, so we're going to do the exact same thing, only now I'm dealing with h of x, which is my purple one. So my purple and my red, which is k of x. What I'm going to do is, again, I look at my purple, and what's that equal to? That's equal to x squared, so that becomes x squared. My plus sign stays the same, and my k of x, my red, becomes 2x squared plus x minus 3. So after this, I can go through and I can collect my like terms. I see a like term set here with the x squared and 2x. If you want to put a 1 there, imaginary 1, to make sure you remember or know that it's added together, it gives you 3x squareds. You have an x, but it doesn't have a partner. Very sad. And you have a minus 3, doesn't have a partner as well. So it is what it is. That is your fully simplified form. Again, please note that there is not an equal sign here, so you're not solving anything. You are just simplifying it. That's all. Okay, going through this one a little bit quicker. There is a little bit of a difference to this. So we have our h of x, which is our purple. That doesn't change in terms of the way that I do it. But the f of x does, and you'll see why in a second. The main reason is because you have this minus sign here. So I'm going to do exactly what I did before, and I'm going to take my h of x, which is x squared. So I do that the same. I have my minus sign, but what I need to do is I need to make sure that I compensate for that minus sign. So I'm going to put a parenthesis set. You can do this with positive as well. Like, for example, if you really wanted to, you could put a parenthesis set to kind of indicate that that's the function that you're adding. But the reason you need to do it here is when I plug in f of x, well, what do I have to do with that negative? And it's an imaginary negative 1 if you want to put that outside. I have to use the distributive property. So distributive property, to simplify this, I would get x squared minus 3x minus 6. I don't have any like terms, so I'm done. But the main thing that's different from this is you have a minus sign, so that has to be compensated by doing distributive property. A common mistake is people do not put the parentheses and they forget to distribute the negative 1 to the 6, and they end up putting plus 6 for the answer, which is incorrect. So you need to make sure that you have that negative sign distributed all the way through. Okay, so continuing on, we're going to do another h of x here. So I have my h of x, which is equivalent to my x squared, and I have my k of x. So my h of x is x squared. My k of x is the 2x squared plus x minus 3. So I have to do the minus sign, and I'm going to do the parentheses because, again, you have a negative, and you have the 2x squared plus x minus 3. Okay, I'm going to do another technique here, which is basically taking the minus sign and doing a positive and then changing the signs of each one of the parts or the monomials inside the parentheses, so that, this is just another technique. So instead of rewriting the whole thing, you now have all the signs. For example, x squared and minus 2x squared become negative x squared. The negative x just stays negative x because he doesn't have a partner. The positive 3 stays positive 3, and he doesn't have a partner either. So we just simplify it to negative x squared minus x plus 3, which is your final answer, simplified. All right, so this one, gotta love this one, and you'll see why in a few seconds. F of x, that's my blue one. So I've got my blue, that's going to be equivalent to my 3x plus 6. I'm putting parentheses around this, and you'll see why in a second. It's mainly because of this guy right here. So I got my k of x is my red. So my red k of x becomes the 2x squared plus x minus 3. Reason I said this was all sorts of fun is because if you notice, remember from Algebra 1, this is the only thing that's Algebra 2, taking the f of x and k of x and plugging it in. That's it. Everything else is Algebra 1 material. So if you look at this, the best analogy I have is think of the 2x squared plus x minus 3. Think of them as like a house, and the 3x plus 6 are people trying to get into the house because maybe the 2x squared plus x minus 3 are having a party, and they want to get into a party. So what do the 3x and the positive 6 have to do? Well, let's say the 3x goes first. He has to greet every single person in the house. This is the distributive property. You can think of it as what's called the double distributive property. If you don't like the house party analogy, fine by me. Pick and choose double distributive property is fine also. But what I'm going to do is I'm going to multiply the 3x and the 2x squared. I'm going to do 3x just to kind of show what I'm multiplying. 2x squared. I put a plus, and now I'm going to do the next part. 3x and x. I put a plus. I always put a plus just because you'll compensate for the signs later. Then I got the 3x and the negative 3. And now I'm going to move on to the 6. So instead of doing, so the 3x went high, so the 6 is going to go low. So maybe he gives like handshakes instead of high fives like the 3x does. So I do plus. My 6 goes to 2x squared. Plus, always plus. The 6 now goes to the x. And last but certainly not least, the 6 now goes to the negative 3. And I just made it in terms of size. Awesome. So now I'm going to simplify this. You do not have to write this entire long polynomial if you do not want. If you want to do 3x times 2x squared and just write out what it is, 6x to the third, I'm fine with that. The reason I'm doing this is just to show what maybe you haven't seen for a little while in Algebra 1. So that one's taken care of. We got the plus 3x squared. Because remember, you add the exponents when you're multiplying two numbers that have the same base or two variables that have the same base. We have the 3 and the minus 3x and the minus 3, which gives you negative 9x. We have the plus 12x squared. Go through this a little bit quicker. Plus 6x and minus 18. Now I can collect my like terms. My 6x to the third, he don't got nobody, so he just stays the same. The 3x squared, he's a like term set with the 12x squared, so we say that that is a 15x squared, not 15x to the fourth, which is what some people do because they add the exponents. That is incorrect. That's a wrong thing to do. We got the negative 9x, the positive 6x, which gives you negative 3x. And then last but certainly not least, we got the negative 18, and he does not have a partner, so we got minus 18. I should be distinguishing these so that they look different, so that's my bad. But once we get through this, that is your finished final result. It's not pretty, but it is what it is. This is why this problem, which you will see on quizzes and tests, can be time-consuming. But if you break it down, the only thing that's Algebra 2 is right here. Everything else, this is Algebra 1. So if you're having trouble with that, it's not your Algebra 2 skills. It's your Algebra 1. So, all right, let's do a slightly easier one. I think this is easier. You can pause the video and try this one on your own if you would like. But again, I'm going to kind of go through this step by step. We have our h of x, which is my purple. Then I got my g of x, which is my yellow. And I just substitute what those are equivalent to. So my purple, my h of x, is x squared. I have my g of x, which I'm going to put in parentheses. That is going to be x plus 2. And in this, all you do is distribute. Much nicer, much easier than the last one, and I'm going to not multiply or show what is being multiplied. I'm just going to go through and say this is x to the third plus 2x squared, because I just multiplied straight through and through. That is my distributive property. Okay, so the next topic of conversation is going to be the composition of these functions. So we added, subtracted, multiplied. I did not give an example of dividing, but that should be pretty straightforward because you're doing the exact same type of stuff. But the thing that's different about compositions, if you notice in multiplying, that was a filled-in circle. Now we have an open circle. And what this basically is, composition is a compilation putting together two functions in a certain way. And what this is basically this reads g of f of x. And how this goes, you basically, what I tell my kids to do is they have f of x. You work from the inside out. If you work from the inside out, the problem will be significantly easier. Once you evaluate what the f of x is and establish what that is, you will plug that into your g of x. So first evaluate the f of x, then use f of x as the input, plugging in what you're plugging in for the g. Probably people are looking at this, if you're looking at this for the first time and you're like, what is going on? Well, it's going to take an example or two to kind of get this in your mind. So let's jump right in. So here we go. I've got my a of b of 2. So what I did is I rewrote this in terms of the function form from this previous slide. The only difference is instead of having x here, or x here, we now have a number. So what I'm going to do, if you notice, I just replaced, so it's a of b of 2. So what we have to figure out first is what b of 2 is. So what I do is I say b of 2 equals, so I look at this, my x here is becoming 2, so that means this is going to be a placeholder 3 times your 2. What I basically tell people is that if it makes a little more sense, you think of b of something equals 3 times whatever that something is. All I did is I replaced my x value here with 2. So this guy, instead of being b of x, is b of 2, and I evaluate it. This becomes 6. So now, this entire part here, this b of 2 actually becomes, we evaluated it as 6. So I just established that this is number 1. We're going to now do number 2. Okay, so I take my a function here, and I'm replacing my x. My x becomes a placeholder. But what goes in that placeholder is going to be your 6, the number 6 that you evaluated. So that goes here, which means it goes here and here as well. So what this is saying is that the function a of 6 is going to be equivalent to 36 plus 12, which equals 48. So all you're doing is just manipulating the function. This will become a little more evident when you practice it, but if you don't practice it, this is going to be difficult for you. But notice I did it in 2 steps. Okay, so I'm going to do the next one, which is d of c of 4. So we have d of, and c, which is in purple, of 4. So now I've got it color-coded. First thing I got to do is I got to do the inside part here, which is c of 4. So c of 4 is equivalent to 2 of 4, quantity squared, minus 6 of 4. Where am I getting this from? I'm getting it from right here. My x values, I could easily replace all of these with x values, and it would be the exact same thing as this guy right here. But since I know that my value that's in place of the x is 4, I'm going to place 4 into each one of these x placeholders. Now I evaluate this. I do the exponent first, and then I multiply by 2 from here, so distributing. So that gives me 32, so 16 times 2 is 32, minus 24. That gives me 8. So the second thing I have to do is I have to take d of my placeholder, which is 2 times my placeholder minus 8. Well, what goes in the placeholder? Well, since this purple became 8, that means it's going to become 8 and 8. And where is that purple from? Where is that 8 from? It's from right here. We evaluated c of 4, and that means c of 4's equivalent of 8 is going to go into the placeholder where c of 4 was. So that's where that goes. So now I evaluate this. I get 16 minus 8, and that gives you 8. That is your final answer. Okay, so going through a little bit quicker, if you'd like to pause the video and try this on your own, you're more than welcome to, but I'm going to go through this. We have B of, and I have C of negative 3. Okay, so what I'm going to do is I'm going to first do C of negative 3. That's equivalent to, notice I'm taking away the placeholder here. I'm just going to go for it and do 2 of negative 3, quantity squared, minus 6 of negative 3. If I evaluate this, I got 9 times 2, which is 18. I'm doing order of operations, and since the negative 3 is in parentheses, that's a positive. Negative and negative become a positive. You got positive 18, so this evaluates to 36. So this purple part here in the second step is now going to become, second step, B of 36. So we have B, which is 3 times 36, which gives you 108, and you are done. So in 2 steps, again, I work from the inside out. And the color coding really helps. So if you want to do these with colored pencils, it might help you for the first few times to do it so that it makes a little more sense. Okay, so I'm going to do this one. I'm going to do it kind of the exact same way, a little bit faster. So we got A of, and we have B of M. Now, here is the interesting thing. In this case, we don't have a number. We actually have a variable. In this case, the variable is just going to be placed into the function, just like a number is. So we're going to do this. I have to still first do the inside, which is B of M. So B of placeholder M becomes 3 times, what's my placeholder? Well, it's 3 times M. So that means my B of M is equal to 3M. It's not a number. It's not nice, but it is what it is. Welcome to Algebra 2. So now you have to use that in the second step, A of, now we have to do 3M. So in this case, what I do is I say that I have my 3M quantity squared, so I'm putting my placeholder plus 2 times my M, or my 3M, because again, that is going into each one of the place values where the x is in the A of x function. So once you do that, now you have to simplify, distribute the squared. You got 9m squared plus 6m, and you are done. That is it. Okay, we're going to do this one, and this kind of looks a little confusing because you're basically doing d of x, which is kind of on the odd side of things. So we're going to do d of x. So I'm going to try this a little bit differently. We know that d of x is equal to 2x minus 8. So that means this d of x, so my first step, is going to become 2x minus 8. So now, what I'm going to do is I'm going to take this d of x and plug it into the value of x for my d of x. Kind of seems redundant, but it literally is going to give you a different function. So now we have my d of x, which is 2x minus 8. d of 2x minus 8 is going to become 2 times your placeholder minus 8. Well, what is my placeholder? It's 2x minus 8. And now you simplify. Distribute. We got 2x times 2 gives you 4x minus 16 minus 8 minus 24, and I'm done. That is it. That is all. Okay, last but certainly not least, we're going to do b of d of z. So in this case, we have b of d of z. I'm going to not do this with the color coding because you're going to want to eventually get to the point of not doing the color coding. So I'm just going to kind of go through the way that you need to be a little bit quicker with. But if it doesn't make sense, look at the way the color coding is, and you're more than welcome to use that. So what I'm doing is I'm using d of z. So b of d of z, which is 2x minus 8. So that means I'm going to plug in z for my x value. And now, that's the first step. The second step is to take this value and plug it in for every value of x that I see for b. So b of 2z minus 8, there's a minus there, equals 3 times my place value holder, which is 2z minus 8. Distributive property, we got 6z minus 24, and we are done.